Let's talk about space. It is getting seriously crowded up there. Not just with individual satellites, but with these incredible interconnected swarms of them all working together. But here's the million-dollar question. What happens when one of them goes rogue? Well, today, we're diving into some amazing research that's created a kind of high-tech detective to find these hidden faults before they can cause a total catastrophe. Okay, so take a look at this network. It's a really complex web of communication, right? Now, I want you to imagine that two of these satellites, they're secretly developing some serious problems. They're still talking to their neighbors, sure, but the information they're sending out is bad. And the real challenge here isn't just finding them, it's finding them while they're buried in all the noise of a dynamic, constantly talking system.
So, to really get a handle on the solution, we first need to understand the crime scene. These clusters of satellites, or what engineers call multi-agent systems, they are the absolute backbone of our future in space. They're going to work together on everything from watching our planet to beaming internet everywhere. But their greatest strength, their connectivity, well, it's also their greatest weakness.
You see, a fault in a system like this isn't just some isolated event. Because these satellites are constantly sharing information, a little hiccup in one unit can spread through the whole network. It's kind of like a virus that can corrupt the data of the entire swarm, and that could potentially lead to a total system failure. So yeah, finding these things early, absolutely critical.
So, how in the world do you catch this ghost in the machine? The brilliant solution that this research came up with is a specialized algorithm, one that's designed to act like a digital detective, hunting for clues hidden deep inside the network's data stream. This detective is called an Unknown Input Observer, or UIO for short. And think of it this way. A satellite swarm is constantly getting pushed around by known disturbances, little things like gravitational poles or solar winds. The UIO's whole job is to look at all the data coming out of the system and skillfully separate the red herrings, those known disturbances, from the real clues that point to an unknown hidden fault. Okay, so the researchers first tested their detective on a more, let's call it a straightforward case. This is the ideal scenario, really, where the clues are clean and the culprit is much, much easier to spot. Let's see how that works.
Now, in engineering terms, this is called the matching condition. It's basically the perfect situation, where all that background noise affects the system in a really predictable way. This lets the UIO just completely filter it out, perfectly separating the fault signal from everything else. And what you're left with is a crystal clear piece of evidence.
But of course, space is rarely that neat and tidy. That would be too easy, right? So next, the team tackled a much more realistic, much more difficult scenario. One where the evidence is messy and all the clues are just tangled up together.
And this just lays out the difference perfectly. In the messy case, that matching condition we talked about, it's not met. The disturbances are all tangled up with the satellite's own internal dynamics. You can't just filter them out cleanly anymore. A standard UIO detective really struggles here. It literally can't tell the difference between a red herring and a real clue.
So the crucial point is that in this more complex, more realistic scenario, our detective needs an upgrade. It needs a brand new technique to see through all that fog and pinpoint the fault when the standard methods just aren't going to cut it. And this is where the core innovation of this research really shines.
And that superpower is what I'm calling the energy fingerprint technique. The technical name for it is dissipative theory. And it's this really cool concept borrowed from physics that lets our detective perform a kind of energy-based forensic analysis on the entire system.
So what on earth is dissipativity theory? Well, in simple terms, any healthy dynamic system has a predictable energy balance. It takes in energy, it stores it, and it gives it off in a really consistent way. You can almost think of it as the system's normal resting heartbeat. This theory just gives us a mathematical way to track that flow of energy. This whole forensic process is just brilliant. Here's how it goes. First, the UIO establishes a baseline. It learns the normal energy flow, that heartbeat of the satellite swarm. Then, when a fault happens in one of the satellites, it disrupts this flow. It breaks the energy balance. And this disruption, it creates a unique signature, an energy fingerprint that the observer can spot immediately. It's no longer even looking for the fault itself, but for the effect of the fault on the system's energy. So clever. So, the big question. Does it actually work? Well, let's look at the evidence from the simulations. The researchers set up a network of 7 satellites and then secretly introduced some hidden faults just to see if their super detective could solve the case. So here's our crime scene again.
In this simulation, the researchers switched on these fast, time-varying faults in satellite number 2 and satellite number 4. The other 5, they're totally healthy. The goal is for the diagnostic system to find these 2 culprits and only these 2.
And boom, here's the first piece of evidence. This graph shows the fault in satellite number 2. The blue line, that's the actual secret fault the researchers put in. The red line, that's what the UIO estimated the fault to be. I mean, just look at how perfectly it tracks. Even with all the system noise and disturbances, the detective found the culprit and correctly figured out its behavior over time. Amazing!
And here's the second piece of evidence, this one from satellite 4. And again, a nearly perfect match. The blue line is the actual fault, and the red line is the observer's guess. This basically confirms the technique works across different satellites and for different kinds of fault signals. Our detective has successfully identified both culprits.
Okay, now, here's the most incredible, the most mind-blowing part of this whole investigation. How many satellites needed to have this powerful UIO observer installed to monitor the entire network of 7? Just 1. That's it. All of this complex fault diagnosis was done by a single observer sitting on satellite number 3. It was able to diagnose faults in its neighbors just by listening to the network's chatter. Unbelievable.
And for the final verdict, the researchers compared their new energy fingerprint method to another advanced detection technique. And the results show that while both methods are pretty good, the energy fingerprint approach is noticeably more precise. It has a smaller estimation error. So, case closed.
So, what are the big takeaways here? First, we've got a new diagnostic system that can handle both the simple and the really complex, messy scenarios. Second, it uses that innovative energy fingerprint method to find faults even when they're buried in noise. On top of all that, it is incredibly efficient, letting us monitor huge networks with way less computing power. Ultimately, this is a major step toward making those satellite swarms we all depend on way more robust and reliable.
This research gives us a powerful new tool for sure, but it also leaves us with a bigger question. As we build more and more of these complex, interconnected systems, not just up in space, but right here on Earth, the challenge of making sure they're reliable is only going to get bigger. It really makes you wonder, what other hidden vulnerabilities are we creating, and what other clever detectives will we need to invent next?